Welcome to Pratidwani, where we try to humanize science. I'm your host, GV Pawan Kumar. It is my delight and pleasure to introduce you to my guest on this episode, Joyee Ghosh. Joyee is a professor at Indian Institute of Technology, Delhi, and she's a quantum photonics researcher and experimental physicist, and has done some fascinating research, uh, including quantum mechanics and optics, and bringing them together on a single platform. She's also been asking interesting questions related to various important concepts related to entangled photons and how to utilize them for various different operations, right from fundamental physics and also nowadays to develop new interesting technologies. So, with this very brief introduction, I'll welcome Joy on Pratidwani.
Thank you. Thank you, Pawan, for having me. I'm
Yeah,
glad to be here. So, yeah.
delighted. Joy, give us a gist of how you got interested in science and what was the kind of upbringing you had in your childhood and what really led you to science and studies in science and later on becoming a scientist.
Okay. So, Pawan, actually, my upbringing was from a very simple family. I'm from Calcutta, and I was raised, born and brought up in Calcutta. Went to a school called Calcutta Girls High School. Both my parents, so apparently, there's no academician from our family as such, from the nuclear family, but both my parents studied science. So my mother was a student of anthropology, and my father was very good in science and geometry. So from my childhood days, I remember my school days at home. I used to learn a lot from my mom and maths from my dad. And school was very special. So I think a lot of my upbringing and the kind of person I am, everything school has a lot of shaping there. So so my studies are all in mostly all in Calcutta, the formative years. So it was Calcutta Girls High School, and later on Lady Brabant College, where I did physics honors, BSc. And then after that, I moved to Delhi in JNU for my master's in physics again. And after, so in JNU, I also completed my PhD, which was partly in collaboration with in France in a CNRS lab. So I have two supervisors there, and I think these are the formative years, and after that, there are several postdocs, or three postdocs to mention. So I uh, went around the world a bit, starting actually also during my PhD, I did my experiments in Paris, in Orsayville rather. So that's the thing. Um, so what? So I think if I have to start from my school days, right? I mean, like there were different kinds of subjects, of course, but science and maths always interested me, and particularly I was very fond of physics right from the beginning. So during this cusp of class 7 and 8, where 6 and 7, where you're having this division, science breaks up into these three parts. So bio, chemistry, and physics. I remember, maybe things used to flow very logically, and I was a more of a mediocre student before that. But physics, I think, with that, I had a lot of excitement in life. Even for the simplest of things, heat and electricity and all those things that we were learning. And our teacher was very interactive, and she used to ask gave us homeworks, and we used to find answers, and things flowed in very logically. So I think that was the starting of my interest in physics, which really, never went. So it was always up, up, up. And if I had to compare all the three subjects, of course, physics was always my favorite. So I scored very well because I think I understood it, and that all of that gives you the encouragement. So that is it. Yeah.
Wonderful, wonderful. So, Kolkata also is a place where basic science actually is considered very on a higher pedestal, at least in the past. So, how was the kind of environment in your school and college? Did that really have a deep influence on you becoming a physicist, or was it slightly later than you picked it up?
No, no. Physics was the interest in physics was right from school. In fact, there are some interesting twists and turns in life, and I
Mhm.
think it's really. I have always followed my heart, and so I'll come to that. But
Yes, yes.
before that, so I think it really started for me in school right away. For physics, it was the most interesting subject, I think, compared to any other. Of course, maths was also one of my favorites. There was computer science, which I was into, and the softer parts, I was also fond of English. Geography was also another favorite ones. So those were the things. Um, so if I have to talk about, so school gave a very vibrant, like a very exciting atmosphere
Mm.
because there used to be competitions. We also had these special summer camps and winter camps where we were, so a group of students were selected. I remember I went there for these programs. I went 3 times from my school, being selected out of a group, and I went to camps in the Birla Institute of Technological Museum. So that's
Mhm.
that's uh, that's one part, and some students are always selected every year, sort of. So this starts from class 7, 8, 9. Those are the years. So I went once for physics camp, for chemistry camp. Then there was a special camp for computer science. Those were the days, we were learning. We had our practical classes also. So yeah, I think BITM, those special interactions with peer groups, and particularly fueled with teachers who were also young and very interesting. They used to come up with problems, and they also gave us opportunities where we could go and learn more than what's there in the syllabus. So I think that those gave us some opportunity, and the environment, kind of where you can grow to love the subject even more. I would say that. And then later on, so in Lady Brabon College, physics honors 3 years was actually pretty. So the syllabus, I think, was huge
Mm.
with our practicals and everything, and it used to be very interesting because it was like a deeper thing into physics. What we learned from school, I was already like mesmerized, and in this huge syllabus of physics honors, with along with the practical, I think the syllabus was very good. So yeah.
You had very good teachers during that time. You generally had a good.
Mostly, yeah,
Mhm.
mostly good teachers, I would say. Mostly good teachers, particularly teacher in optics who taught us optics
Mhm.
was very good. Huh? Goridi, and I remember. So it's really your formative years. I think later on we come across names which are much bigger,
Yeah,
but
yeah.
I think in these initial years it makes an impact on the mind. So I remember this particular teacher. We used to call her Goridi,
Mm.
and she really lit up the because it was all physics honors, so there were different streams as you can gauge it. But optics was really fascinating. She made us really understand it also, posed it, took all the lectures, made the concepts very easily, um, um, absorbable in some
Mm.
way.
Mm.
Right? Those were new things we were learning. Lots of maths also, right, at the background of all of that. And understanding each and so like polarization, starting from the very simple concepts, laser
Mm.
physics,
Mm.
So, and all the books that we followed. The library was also good. So those were the days where we went to the library and, because once a lecture would be taken, there would be several doubts, and then
Mm.
we had to clarify before the next lecture. And so strictly speaking, not school homework, but you have to clarify your understanding. So it was an oldish kind of a library, and we could take home books, and and some of us, so we were a small group, and some topics, somebody understood, some practical where we would, some of us, we were just trying to do it probably routinely, while some others, took a little deeper thought. Then
Mhm.
we exchanged ideas in our canteen times. So in order to understand it, so CRO, cathode ray
Mm.
oscilloscope. So we
Mm.
had all those experiments. And then also in MSc, we had experiments where, talking to our friends and all was, I think really also that was, apart from the teachers, of course, who gave us our
Absolutely,
classroom
absolutely.
lectures. I think we
Yeah,
learned a lot even by reading.
yeah.
So library, and of course now we have internet, so kind of everything is accessible. But there, those were the days also where we so of course we had our own set of textbooks always, but going to the library and hunting for a book that is, that would actually answer your questions or answer in a very, nice way. All the good books, I would say. So
Wonderful. In
I
fact,
felt like physics.
that's something very fascinating about learning optics, because it also has a very rich history, in the sense
Hmm.
there is so much of
Very rich.
content. And also the education in optics starts at a very early age. It's also very visual, because
Hmm.
demonstrations, experiments, etc. What you do, you learn it at a very early age. But as you progress in schools, colleges, and etc., you will see that it actually kind of diversifies, and it goes quite a bit in very very different directions. Especially if you're going from a physics angle, then you will start looking at electromagnetism, optics, and other things together.
Much later
Uh,
we get to see the cusp with electromagnetism and so on. Initially
Correct.
we read them as, different parts, like different
Parts.
subjects, but within physics. But later on we see the angle, and then everything. Then you unify everything with quantum optics. You start from. So that's another.
Uh, Another thing. I'll come to that part, because I'm very curious. Also, being in the tribe of optics, I'm always interested in knowing how people really got interested, and also got trained in quantum mechanics, and
Huh.
club that with optics. Because our deep understanding of quantum mechanics essentially comes from some of the measurements in optics and quantum optics.
Hmm.
And I would come to that part of it. But before that, I would also want to kind of explore a little bit about understanding the kind of physics education you had, both in terms of your schooling and college. How was it? What kind of foundation you got during these times, especially in terms of experimental science, because you are an experimentalist, and which means that you will not be able to just become an experimentalist just going into a laboratory in your PhD. You will have to have that, inclination towards, using your hands and your brains. I keep telling this. Experimental physics is using both hands and brains together, right? And I just am curious to know about this, Joy, because how did you really develop that intuition and also inclination towards doing experimental physics? What part of your foundations was very important? Could you just let us know?
Um. So I don't know the eagerness to ask why, why a
Hmm.
particular thing is happening, starting from raindrops or the color of the sky. These are very basic questions. I think many kids do think about these. I used to worry a lot about the rainbow. I loved it and
Yeah.
and then when I actually understood, what causes it and what happens, even the simplest thing, I think in our first class 6, 7, 8 lectures, like when we are starting off with optics, right? We learn about the prism,
Hmm.
right?
Yes.
And
Yes.
the dispersion through it. Those things are fascinating. And when you actually see it with a white light and you see it, it's a very simple tool. Right? You just and then we, of course, we had all those small things in our school labs, starting from those, and then later on, I think more. I mean, like compared to any other, so electronics experiments were also very nice,
Hmm.
and
Hmm.
they were interesting, like different kinds of circuitry that you have to do. But side by side, all these experiments, particularly during our physics honors labs, right? The Fresnel biprism, the Newton's ring experiment,
Hmm.
and I think these were, even the CRO experiment, right? It was difficult to understand initially. Fresnel biprism and all of that was easier, like
Easier.
concept
Yeah.
wise,
Yeah.
right? Young's double slit. I mean, it follows different forms, different ways you can see interference and diffraction. And later on, I think in our masters, a very simple experiment like the single slit diffraction, one would
Hmm.
not think about it, right? This pattern that, and then if you change the size of the slit, right, the pattern, shrinks or it becomes broadened. All these things are at your with very simple things, right? And with your hands, you can actually manipulate. So it's like
Absolutely.
manipulating light. right? So something starting from the sun rays and also the those simple experiments as kids that we do. Like if you have a lens, I remember my grandfather was actually also a science person, and we used to sometimes interact with him, and he told us, why don't you try? So this, I and my sister, we tried it together,
Mhm.
and we didn't want to have an accident, but like, we just kept a paper, and then we had a very thick convex lens from his toolbox. He had a toolbox with, magnifying glass and all of that, and very thick convex lens. And one sunny day, we were just trying this, and we were not successful in the first time. But yeah, initially it did happen, and we saw the paper burning. So all those things were like, very simple things, no nothing, no combinations that you have to do. You just need a paper, and I tell my son the same thing, that he can start doing all these stuff a little bit. He tries his hands on them as well. I think so. All these were very intriguing, I would say.
Fascinating, fascinating. See, that's the part of it, because this is also not generally something which you can put in a curriculum, right?
No,
These are
not
these
really.
right. These are all because I'm always curious about how an experimentalist becomes an experimentalist, because I can understand sometimes you, if you're inclined more towards mathematics,
Hmm.
because which will be part of your education, then you really go deep into
Calculate.
it, calculate and things. I also keep telling that we experimentalists also have to do that, right? Because we also have to do a lot of mathematical stuff, especially experimental physicists. We'll also have to use a lot of mathematics in
Mathematics
addition to
and
that.
theory. And
Yeah,
theory, right?
and
So
theory.
I tell the same here. There are some theory, I mean, like people who are doing theoretical research, some of them want to join hands, and it's beautiful. But
Yeah,
for most of our parts, when we are doing our experiments, and we are stuck with something, and we also want to figure out, what is the, underlying physics behind that.
yeah.
Sometimes things are not, most of the times, actually, things are not behaving well, right? Even a simple waveguide, we are expecting a very symmetric kind of spectra out of it, but what it is giving, is something asymmetric. But we have to understand why it's happening, right? And the hunt for that, no, the quest for that, why it is not following the usual behavior, I was thinking, would, like you would ask you to actually maybe, go back to the theory, chalk it out yourself, write a program, maybe try to fit it. And if it's not fitting, then there's something else that you have to keep adding. So
Adding.
it gives that asymmetry, right? Something like
Absolutely.
that. Or maybe there's something, some focusing lens that we are using. So
Hmm.
recently we discovered, we actually didn't know this very deeply, but in one of these experiments, it's a very simple thing. I would like to share. I don't know if I'm
Yeah,
being
yeah. No, no,
fast.
no. Please do. This is actually the best way to actually take the conversation together. Okay, please go ahead. Please
In
go ahead.
SAG and
Yeah.
SPDC, actually,
Yeah.
we expect these single photon spectra as a
Yeah.
function of
So for the listeners, SHG second harmonic generation, and it's a nonlinear optical process. Just yeah, yeah. Go ahead.
It's
Go
not
ahead.
a nonlinear optical process,
Mm.
and second harmonic generation is actually the classical version of it,
Uh,
and spontaneous parametric down conversion is the quantum version of it,
whatever.
which cannot be explained classically in a way. So we were doing this in the lab, and we started with a very, so this is a few years back, and we started with our crystal and waveguides. And since it was a crystal, right,
Mm.
and with the so the input facet was maybe just 1 millimeter by 1 millimeter, something like that. So you needed tight focusing, right? So there is a laser beam that's coming, and then you have to tightly
Mm.
focus it. And of course, we were using input lens and an output lens. And then we tried to, so in the output, so initially we did SHG, but then in the quantum way, we did, when we were doing SPDC, there was generation of photons, and then we want to measure the photon spectra as a function of the crystal temperature, and we can
Mm.
also do it as a function of wavelength, right? So anyway, so these, we were expecting them to be very symmetrical, and we didn't get a symmetrical pattern, and we also didn't get the efficiency we were wanting. And then of course, so like just tight focusing was not essential. I mean, we know this from Gaussian optics, right? There has to be some kind of a thing. But then there is also from like a very old paper of Boyd, and forgetting the yeah, so Boyd, one of the old papers of Boyd, and also, simple, I think, focusing. physics. So we understood as a function of this zeta, which is the
Mm,
focusing parameter. So the efficiency is actually a balance between this zeta parameter, so which is focusing, and so it's just not tight focusing that is that is going to give you the job, right?
mm,
And if the spectra is symmetrical, then automatically the efficiency is up. But that happens as a function of, the input output lenses
mm,
that we have. So these are simple things. We went back to those, original papers, and somehow we, in the fit of, the bigger things like quantum communication or entanglement and all of
mm,
that, we somehow overlooked this small, optics part. But this was so useful in getting, everything, cranking up the photon number and everything. So that's a small detail that we took care of, but we had to go back. And, simple calculations we did, a simple program, a simple, change of distances, and yeah, I think, and we solved it out. So most of
wonderful.
the time, things are not working in the lab.
Okay,
Then,
absolutely.
yeah.
No, that's just something which I'm also always very fascinated. Yeah, and I keep telling to all the students and also even my coworkers that uh, in the lab, 99% things don't work, but you don't know which is that 1% which works. So in order
And
to
then you
really
have to keep pushing that. Yes.
exactly, exactly, and
And
it's
keep going, then nothing
yeah,
breaks down, because
nothing.
that's another thing in the
Another
lab.
thing. Yeah.
When you're at the cusp or the high of, now we're going to take our data, so the students tell me this. Now everything is fine, ma'am. Tomorrow morning we'll start taking the data. Okay, very good. I mean, I will come and participate and all. But then in the morning, something, I mean, it's also maybe because we are constantly using all those equipment,
Yeah.
they are stressed.
That's
Like, oh,
that's a good one. That's a good one. So, Joy, I also wanted to know a little bit about your evolution as a physicist going forward. After you finish your bachelor's, now you go into JNU physics department, which is actually a very reputed physical sciences department, and also is very well known for theoretical sciences. But you also work
condensed
with
matter theory, I think it's very well known for that.
yeah,
Because
yeah,
of all the teachers we had, and they were all very, I would say, very highly educated from very good, their pedigree was very good.
mm,
Came up with a, ocean of knowledge, each one of
knowledge.
them.
Yeah, yeah,
And it was an honor to, learn from those teachers. So I'm not naming
absolutely.
anyone. I mean, actually, naming any particular one would
Yeah,
not
yeah.
do the suffice the job.
Yeah,
I mean, I think it
absolutely,
was a whole bunch of good teachers. We were fortunate to learn from them.
absolutely, absolutely.
But it
You
was all
also, yeah,
theoretical condensed matter
yeah,
more. Sorry, Pawan.
yeah, yeah,
But
yeah,
I
yeah.
don't know.
Please.
I think my interest in optics started from, I mean, of course, from the school days and from the bachelor days, and it didn't die.
Mm,
Although like the School of Physical Sciences were more of theoretical condensed matter.
correct matter.
And the only lectures we had in, so optics, we didn't have any particular lecture as such, but
Mm,
laser physics.
laser. Okay.
Of course, we had electromagnetic waves, so from J.D. Jackson and all of that. So,
Mm, mm. So then you also worked with Professor Rupa Manjari Ghosh. Then in your PhD, I want to know a little bit more because she is one person, a great kind of researcher whom India should actually know much more than what we are aware of. Could you please tell us your experience of working in her lab, working with her, and
hmm,
also your kind of questions, what you are interested in that particular phase of your research as a PhD scholar?
hmm, hmm. So, actually, being in JNU and from SPS,
Hmm.
initially, right after our masters, I think during our masters, I did a project on nanotechnology. So this
Hmm.
was, so we were exploring the exploding wire technique to produce
Hmm.
nanoparticles in a
Particles.
colloidal solution, right? And this was again a fascinating experiment. But I was again interested in the optics part of
Parts.
this, being the original, I think, that way. Although it was about nanoparticles. So I was working with copper nanoparticles. We made this. So during our MSc project, we made this equipment for this
Hmm.
exploding wire technique. But that was very successful. It was very nice experiment. And then we used to. So one part of that, I think, was to see it under UV light. So the metals look different, of course, and the colloidal solution of these nanoparticles, metallic nanoparticles, they look very different. The colors are different, right? So this is one part which was fascinating. We also had a patent out of that, so it was a successful project, and it naturally uh, turned me towards
Yeah.
that direction. I thought I could start my PhD there. So
Mm.
that's actually where I started my PhD, and with a different professor. And but I think in within a few months, 6 months or so, I think I continued, and then I just, because JNU also gives us this flexibility where we could change and switch if we, let's say, don't get sufficiently uh, what do I say, stimulated.
Mm.
PhD is a 5 year, 6 year long process, right? So that is how I changed to Rupa, and I started with quantum optics, which after that field I think was an ocean
Mm.
of
Mm.
knowledge, and the first few months I felt I know nothing. I didn't have quantum optics actually as a subject in my
Yeah, yeah,
masters, or also during my of course in BSc there was no question, but it was also in masters we didn't have quantum optics as a subject.
yeah. You're
So
right.
it was with Rupa that I first started, of course, learning more about the subject.
Mm. Mm.
So, and of course the basics were there. So if you have the basics with Dirac algebra, like the quantum mechanics, right? So that gives you so you have the tools, and you
Mm.
just have to understand. So that is how I picked up, and I think I learned about Rupa much later, her contribution, her thesis and everything, and the famous person that she worked with,
Mm.
Mandel, right?
Mendel, yeah. Leonard
The,
Mendel actually is one of the person who laid the foundation for experimental quantum optics, right? And
right.
also theoretical in
I
all
think
sense, the whole of quantum optics. So
exactly,
to yeah.
exactly. And I think it was Rupa's experiments along with Hong and Wu. So
Hangenwu,
Hong
yes.
and Wu were her juniors, and
Oh,
it was Rupa. It was in Rupa's thesis that sinusoidal, so the two photon interference that you would see, and the
yes.
speed source, and all of that. So that was, so I think I absorbed this much later
Mm.
after I joined her. So initially she was just our teacher that I knew from MSc, and then I did not know enough about her during those. I would at least say for the first year in my PhD, and then later when I read about her
Mm.
in books, and she was my guide, and of course, and then we talked a lot about it. And yeah, she explained her experiments. I remember asking her several questions on her papers, and yeah, and also starting to know about Mandel and the other experiments, of course, understanding Hongu Mandel experiments and all of that. Yeah, and then you have to build up. So that part of the PhD, I think I learned a lot because I had to do a lot of self study. Since
Mm.
we have
Mm.
a course, and also in discussion with Rupa, because she gave me a very tough problem to crack. Initially,
Mm.
it was a theoretical problem. Unfortunately, actually, the laser in her lab, it was a big laser, but it was not working. We had space. We were actually exploring other uh, small physics, but
Mm.
then good for a collaboration that she had with Fabia, and because I always wanted to, do some kind of a thing. Having read, and I'm also ambitious. I wanted to do something in cutting edge, so wanted to work in quantum storage initially.
Mm. Mm.
So, Fabia's lab and thanks to the collaboration, it was a CIFIPA collaboration that she had, and that gave me the opportunity to actually go and work in a lab that way. But that was semi-classical physics because it was coherent light matter interaction. So it
Mm.
was to look at electromagnetically induced transparency in a simple cell of helium, metastable helium at room temperature. So it was nothing to do with single photons there.
Mm.
So,
Mm.
yeah.
Was it kind of a EIT kind of thing?
Yes, that's
Electromagnetically
right. Yes, that's
induced transparency. Yeah, yeah,
right,
yeah,
right. So
yeah.
coherent population trapping and
Mm.
electromagnetically induced transparency, these are like cousins.
Mm.
They are like brothers. You
Yeah.
know,
Yeah,
you
yeah.
understand one, the physics and the math of all of that. Yeah, again. So, and then you're going to the lab and trying to, actually see it in an experimental, setup. So when I went to France to do that experiment, we started from scratch. Of
Mm.
course, Fabia had ordered a few optical components, but then we started everything from scratch. The helium cell was, of course, there, and yeah. Again, having read so much about EIT and what all it can do, because EIT is a path for quantum storage of light. So you can slow down light through EIT, and you can also stop light in a particular media. So that was again fascinating because I was very much interested. The research topic has to be very interesting for
Interesting.
you to, drag it along for, so
Multiple years.
yeah, multiple years. And also during that time, I think it's a continuous feed in of knowledge that we gain. And, and you have different layers of that. So initial is an understanding. You read all those popular articles, you get very fascinated. And then you get into the deeper ones because you start looking at the references and the back of it, and then it doesn't end, huh? So I remember there were files and files of these papers I had, and I tried to train myself. A lot of self-learning during those times. And of course, a bit of discussion also with peers, but it was more of self-learning, I would say, during those years. Also, and while again, these experiments in the lab, because this was not any routine experiment from a physics lab, right? So this was you trying to build something and do something new out of it, look at the phenomena and all of that. So it was not easy. I used to work long hours, like any of us, I would say, struggle, even with fiber coupling and all of that. And that's how it started. And ultimately, when you see some fruits out of
Yeah,
it, in terms of some result, the first signal for EIT, it was a big thing that time.
fabulous.
Gives you
Fabulous.
I would say a big push. A
Push.
big,
Absolutely. Absolutely. So,
exactly.
Joey, one more
Small,
thing I
small
wanted to,
ones,
yeah,
small ones to start with, Pawan, and then later in postdoc there were bigger ones, and
bigger ones. Yes, yes.
yeah,
That
bigger
is
ones, and it's really a high, I would
right.
say.
Absolutely right. Absolutely. That's actually a very important thing. One more point I want to kind of, ask and also get your thoughts on this. You know, there is a notion, unfortunate notion that experimental science is mainly populated with men. In your case, you actually have done outstanding work, and also you work with very good people. You know, what would you actually give suggestion to everybody, not just men, but everybody, including women, students who want to really get into this? This is a very important thing because this is also a point where one should get motivated to really get into experimental science. Now, because sometimes there is an inhibition, and it is a kind of a wrong inhibition. Could you just tell us a little bit about how you motivated yourself and went ahead? Yeah.
Yeah, I think, Pawan, thanks for that question. But
Mm,
I actually don't worry or think about this question much because
mm.
in my entire career, I never felt that there is, a
Gender. Mm,
no,
mm,
no. Maybe I was fortunate, yeah.
mm.
Neither in my upbringing and neither in my. So it's only thing. This is also something that I like about academics and research, right? If you're good at it, if you can crack it, if you can, intelligently carve your path in a
Mm,
way.
mm.
It is of course fueled by your own passion and own interest, right? So
Absolutely.
I forgot to talk about that cusp because there was a cusp that came in my life where I had to choose between engineering and actual
Ah,
academic. And I will
very
not
nice.
believe it because
Yeah.
my family and of course my
Yeah.
mother that time, I also had lost my father, and
Sorry. Mm,
she really wanted me back in Calcutta. So I had already
mm,
joined MSc in JNU.
mm.
I'm jumping, by the way. Sorry.
Yeah, yeah, yeah. No, please go ahead. Please go ahead. It's very good. It's very nice.
So I had joined in JNU. I really liked the environment, all the teachers, much of the things. I also remember my initial classical mechanics lectures. We had a fabulous teacher, and being trained from Calcutta University, I mean, for once in the class, I mean, among many of the selected students, I think I felt that I understood better
Mm,
than rest, and others came to me for that. But for many of the other cases like particle physics and all, I took help from friends, I
mm.
remember. So uh, um what I was saying, Sorry,
in the
Pawan.
con yeah, in the context of going forward and then trying to build a career out of it, you also had to come back. Your mother was mentioning that you
Yes,
would
yes,
want to,
yes, yeah,
yeah.
yeah. So, and so at that point of time, actually, there was from my BSc results, right? I could also get through Rajabajar Science College, which is a
Mm.
big
Very,
thing
very,
in
very
Calcutta,
big thing, yeah.
well, quite renowned. And I was getting electrical engineering there. But then, I already started loving JNU, the environment, also the broader environment, huh?
Mm.
Just not the physics environment. I was young, and I think, it was a big exposure for me coming
Mm.
to Delhi and, meeting with different kinds of people, also people from other disciplines, just not
Disciplines,
physics.
yeah.
Right. And yeah, so, and then it was a very tough, I think, decision in my life. But I spoke to many people and
Mm.
many of my seniors also, seniors in the family as well. And many of them, of course, suggested that no, you should get back. My mom never, so in our upbringing also, it never happened. Like she never told us, you've got to do this or got to do that. Always, posed the problem and asked us to choose.
That's true,
And
yeah.
I've learned a lot being a parent now. I think I'm still learning a lot from her methods that way. So she never wanted me to just, follow her. She,
Mm.
of course, wanted me back, but yeah. And then it was a tough time to choose. What should I do? The
Mm.
brain
Mm.
and the society and everything was saying that, okay, no, going for engineering would be the
Mm.
natural thing to do. But yeah. But I think what I chose, I just followed my heart because physics, maybe, I don't know, it would have been the broader part of physics, maybe, I got a lot of exposure after that, and also the trajectory, the flexibility, the freedom that physics or research or academics gives you to go around the world, meet different people, go and work in different labs. Maybe I couldn't have had that. I mean,
That,
there's nothing against any kind of profession, but I'm very happy to be where I am, I think.
wonderful, wonderful.
So the
It's
next
a
step would be where we are.
absolutely fantastic.
And coming back to your question, I
Mm.
think we diverted from that.
Yeah,
So I think if you have the passion and if you're good, at least in academics, I don't feel there's a thing. So more power to more girls and women who really want to come to experimental physics. It's nothing like
absolutely.
that. And in my group also, we there are many female
Mm.
students, right? And they're all doing very well.
Yeah,
Also,
even I've had fantastic students in my own group who have done excellent work. They've gone everywhere. The kind of stuff they did in the lab. I'm actually mighty proud of a lot of them who have done fantastic work. And it also is something which is very interesting because optics as a research area is
hmm.
also competing with so many other interesting areas in physics. Condensed matter, high energy, etc.
Oh yeah,
But personally, of course, we are biased to that particular kind of
yes, yeah,
area. It is absolutely fascinating. Anybody who has really got exposed, and most of the people whom I know, including a lot of our own common friends whom we
yes.
actually have, always have this kind of upbringing where the optics is something which you will grow into, right? It is not something one day you will suddenly see. As you also in your own story, it is very evident that you
Yeah.
had that inclination right from the beginning. It's very
Yeah,
similar
I
to
loved optics, huh?
yeah,
And
yeah,
also learning about photons, when we were learning all these things in our MSc classes about fermions and bosons, I know that photons are, bosons, and
bosons,
all the
yeah.
characteristics of bosons that they like to stick to each other, whereas fermions like to be, individualistic. Even as I don't know, I think I'm in love with photons.
No, no, absolutely, absolutely.
Even the
It's
way
a
they are. Yeah.
it's such a fascinating thing. I totally kind of appreciate that particular point. You also now further went ahead, Joey, to explore things in an international arena, and
Mhm.
the first place you moved after you finished your PhD was Institute of Photonic Sciences at Barcelona, where I had also the fortune of being a short kind of a postdoc at some point of time. And give us a gist because you also work with one of the very, very well-known groups, Jorgen Eschner, who now has done some very foundational work in atom optics and other areas of quantum optics. Give us a gist of the kind of problems you worked. You also went with a Marie Curie fellow, which is extremely very, very highly regarded fellowship internationally. Tell us about that process. How did you really get into that? And also, what is the kind of physics you were interested during that time?
Mhm. So actually, after my PhD, so during the last few months of my PhD, like every one of us, we were looking for our postdoc positions,
Mm,
right? And I had these experiments and also some other papers, looking into the theory of EIT and quantum storage and all of that, dark state polariton and all of that.
mm, mm.
So after that, I was looking some one of those. I think like many other students should do this actually. Many of the papers that you like reading, right, and you've learned a lot from those papers. I mean, well, we can apply to those groups, right? So I was doing many
Very
of the
correct.
applications.
Absolutely. Yeah. Mm,
But yeah, so I wrote to one such big person, and
mm,
it was very kind of him to write back and
mm,
saying that, Joey, that I have superannuated, and but I would pass on your CV to other people. And I think it was one of his connections. I think that Jürgen wrote back to me. So he saw my CV, he saw the papers, and he wanted to talk to me. And he invited me to ICFO, to come
mm,
and give a seminar or something like that. Somehow travel was not that easy at that point of time. I was also trying to wrap up my thesis,
mm,
defend, all those things. And then, so we just had a telephonic, I think online interview that we had. And he asked me several questions, all on experimental physics and what I did in the lab, what I learned, and all of that. And then after that, it happened. So that was a good offer. But I also actually, um, so what do I? Um,
in terms of the transition when
In
it was
terms of the
happening.
transition, yeah. So I was also trying to choose, whether because it's a different country, right?
Mm, mm,
Whether
mm,
I should be somewhere in Europe or maybe US. So I was looking also for opportunities there. But
mm,
ultimately, I think, I think I didn't know about the group enough.
mm,
But so initially, I tried to learn from all the papers that you're going to give me, what the group does. And then
mm,
when came to ICFO, just before coming to ICFO, when I was actually going through all the experiments, because till that time I was busy wrapping up and defending my thesis and all of that. But then so it was maybe barely a few weeks time I had, maybe a couple of weeks, when I actually started reading all the papers from that group.
mm,
And there was another fascinating high, because it was intriguing what people were doing, what they were doing actually in that group. So it was this single traptine group of calcium. They could, of course, also trap a
mm,
chain of calcium ions, but a chain of calcium atoms, just in
mm,
one
mm,
trap. And then this entire thing about the Paul trap, the laser
mm,
cooling, what light can again do, yeah, add momentum and cool down and all of that. And then from a chain of ions to a single ion, and then they're trying to try to do this interaction between a single atom or a single ion and a single photon. So
mm.
it was like all single at the single quantum level. So again, fascinating physics, and something that you want to see in the lab, right? With of course, of all the technological challenges that it has. So I understood that it's another jump that I'm going to, so better get a little prepared, but you're never prepared, particularly for experimental physics. Because when I went there, it was, of course, two, three labs, very complex.
Mm,
And so the photons were in one lab in some way, the single photons that
mm,
we were trying to emit, and the single ion was in another lab. And then there was a third lab with other experiments. So Yoga National's group was a big group again. It
yeah,
was a
yeah.
huge group compared to what I did, and like in my PhD times and all. And again, it was a shift, I would say.
Wonderful,
So
wonderful.
in the environment of ICFO, as you know, again, now there is everything is
Mm.
optics, right? And yeah, and I think ICFO also gives you a big exposure. So
Mm,
all these quantum journal clubs that we had, and within the group discussions, starting to learn about the experiments. Again, very technologically, so all Germans mostly in that.
yes, yeah.
And very tough group meetings also. Where, so first few group meetings, of course, I was all shut, and then later on, I had some chance to
Sure,
contribute. I think to tell, okay, I saw this. This is something that I did. So initially, I was working with a few people who were already there.
mm,
So
mm.
all the people that I learned from a lot, and then I was
Wonderful.
in charge of that experiment, and yeah. But again, learning, self-learning, of
Mm.
course, discussing with researchers in that same group and also outside in the journal clubs and all, discussion with Jorgen. He was I think, yeah, I mean, gave us a lot of opportunity, starting from the Marie Curie Fellowship, and also because I was a postdoc, so I was expected to go and give these. So any most of these conferences, I think I was like the spokesperson. So he
Mm.
banked on my English skills and go and present. So I think it was a beautiful platform to
Wonderful.
communicate what you were doing. And yeah, they were doing fascinating physics. I was part of it. I was happy to be part of it. And then later, I think I became eligible, or I was qualified to contribute something and get something out of it, where I had my papers.
Fantastic, fantastic. So subsequently, you also got a Humboldt Fellowship and went to Germany. Very
Yeah.
unique because I know very few people who have got both Marie Curie and Humboldt. You are one of the few people. With these are all extremely prestigious postdoctoral fellowships. Also gives you mobility and also a great kind of exposure to a lot of interesting things. So if students who are listening to this, especially PhD kind of scholars, these are the things which you can aspire to really take up in future. So Joy, I also wanted to know your experience of having first worked in Europe, where you spent time in Spain and also in Germany, and subsequently you also went to US, where you again worked with one of the very big groups where literally Nobel laureates actually come out on a very regular basis, which is the Joint Quantum Institution at the University of Maryland, which is also closely collaborating kind of venture with National Institute of Standards and Technology, which is NIST,
Yes.
which is again in Maryland. So give us a gist about the contrast of working in Europe and in US, and you having come from India. It is always a fascinating thing because even I have kind of similar exposure, but not to the large extent as you had. Uh, can you give us a gist about your experience of having worked in all these different parts of the or different continents, literally?
Mhm. So yeah, it was in terms of an experience. I think an exposure. It was very enriching. I
Hmm.
would say also starting from the Indian education background that
Yeah.
I had, and going to the work. So the first time I went abroad was actually in Paris for my experiments during the PhD days for
Hmm.
EIT.
Yeah, yeah.
Then I was again back in Europe, but in Spain this time, and then later on in Germany for in Jorgen's group. So actually, Jorgen's group was shifting to Germany, so we had to get some. So I think that was the time I applied for the Humboldt, and that's how I moved to his group.
Hmm.
But the experiments were the same, right? And of course, it was another level of things that we were trying to
Hmm.
look at. So we looked at. I'm speaking a little bit about the physics part of it
Yeah.
because in IFO, I think we were so this is also a beautiful part. People usually, look at or try to understand the physics from the emission of light.
Yeah.
But it's very tough to image or understand or see experimentally the absorption of light,
Hmm.
especially if it is at the single photon level. So emission in terms of a single photon is probably easy to
Absolutely.
see. You
Yeah.
can also have them on a beam splitter,
Beams.
see those anti-bunching experiments and all of that. But clearly absorption at the single photon level, and when the atoms are doing a quantum jump between
Mm.
an excited state and sorry from a
Grounds.
ground state to an excited state on absorption, clearly preparing the atoms and all of that. So all those things were like I think this is some part. I mean, if the this for the students, this is intriguing. And I was also a student or a researcher, young researcher that time. So that was That was one thing. So if you ask me very honestly, my overlap with or my research stay in Europe was actually much longer compared to the
Mm,
short stay that I had in US. So
mm,
in US, when I went to NIST, it was of course a very prestigious position and working in a again a very nice group. Alan was very sweet, and it was a very again a challenging project on quantum eraser, but pretty much with the same background. So I had the background, but unfortunately, I didn't have a very big time in
mm,
US to
mm,
really, get the idea of it. So, like it was a small exposure. It was
mm,
only,
mm.
I mean, I would hardly a year. So, compared to that, the exposure in Europe was
Europe was much longer. Yeah.
the working styles in the lab. I would say, particularly if you are doing experimental quantum optics or
Mm, mm,
experimental
mm,
physics in
mm.
general,
Yeah.
I think it's pretty much the same. Right?
Same. Yeah.
So you
Yeah. You're
have
right.
your own flexible hours. Actually, nobody, I think, interferes. If you want to work at night, if you want to work. So, I mean, in NIST, of course, working at
Yeah.
night and working beyond office hours was a little difficult
Mm.
because of all the security. But
Security. Yeah.
entering
Yeah.
into NIST, every day we had a special, so we had our own these RFID cards
Mm,
and
mm,
all, and used to be tagged. So NIST, in terms of flexibility of working hours, was not that high.
mm.
But then once you're in the lab, and even though the time is restricted, I mean, in within the lab, it's pretty much the same.
Same.
So you have to just pick up stuff from like off the shelf stuff,
Mm.
make your own experimental setup, and yeah, I mean, there the mind is free, and you're not in any.
I-
So
Absolutely.
and I think beyond that, so that working style is the same, I would say. Life beyond the lab, especially like the weekend culture and all, of course, I felt Europe is much more
Yeah.
happy.
Yeah. Yeah. Absolutely.
Of
I
all the
agree with
places
you.
I've been, like Paris and Barcelona,
Uh,
Germany, although we were in a
uh,
smaller place, it was in Saarbrücken, but it
mm.
was very close to the Paris border, right?
Oh, okay. Okay. Is it okay? I didn't know
Yeah,
that.
yeah, yeah.
So you could
So,
always squeeze into that
yeah,
place
yeah.
and everything.
And then
Fascinating.
and
Yeah.
public transport and all,
Yeah.
it's
That's the thing.
easy to travel in Europe. So that's the part I
Absolutely.
really enjoyed. I think I could go around much more. And
But
in
yeah.
US, I didn't have a very big time to, start buying a car and
Car. Yeah.
travel
Yeah.
on my own. So I didn't have such a big time.
Big
It was
time. Okay.
barely a year. And then I just got the offer from IIT Delhi and
Yeah.
wanted to, yeah.
Got it. Yeah. So tell us about the transition and how you started your group and what questions you are now interested in. Give us a gist of that particular aspect. Yeah. And
So
you've been more than now a decade at IIT
yeah,
Delhi.
yeah,
Yeah.
yeah,
Yeah.
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 It's more than a decade now.
Yeah.
It's 11 years now that I've completed in IIT Delhi. So initially when I joined, so it was um, so I think starting from my postdoc year, so that was like 4 years, and then one more year, I would say roughly like that, 4.5, so 5 years of that. I was doing single photons doing several activities. What all the things that they can do, the
Mm.
fascinating thing. So that was a natural thing for me to start my research area there. And I thought, by that time, um, I was very comfortable with SPDC and also the simple setups that you can start with. I did not want to start with something very big initially because you also require funds and all. So
Understand.
ideally, I mean, we get started with a very small seed money, which is, if you, I mean, like we know as experimental physics, I
Yeah.
mean, it's really peanuts. So you have to gather. I think the first challenge or challenge, I would say, or the first, the problem of setting up my own group was to get a space. IT Delhi also has a space
Mm.
uh, issue, right? I mean, it's in the middle, in the heart of the city, and
GT. Yeah. Yeah.
so getting a space in the department to start my own lab because I'm not a purely theoretical person.
Mm.
I was, struggling to start my experimental things. But then you need two things. One is space and one is money.
Mm.
So, yeah, I think
Yeah.
the first few years were all about writing projects, going to different agencies to ask for money like DRDO, DST, all kinds of, SERB and all of that. I started with my SERP project, the EMR project. And of course, the IT gave us a seed money, a very small amount. That's how it started. And I knew that I would not start with something very big because it would require very big funding, which I wouldn't be able to, who would trust a new assistant professor? Which agency would just give you crores?
Mm.
Nobody would,
Yeah.
right? You have to
Yeah.
prove yourself. There's proving at every level.
Very well. Absolutely. Yeah.
So
Yeah.
that's
Yeah.
how I thought I would start. And SPTC is a small thing, and of course, single photon detectors and all, they are all very expensive. So I could only start with one or two, and not even a correlator at that point of time. So just started doing. Yeah, that's how. I think it was easier. And then now with some funding, of course, I also have. So we do several things now in the group, so just not SPDC. So based on SPDC, of course, we have fiber based quantum communication,
Mm.
free space quantum communication, as you already know. And then but I when I had a little bit of platform, I always wanted to go back what I did
Mm.
also in my PhD. So that is also something that we have in the lab now, probing coherent light matter interaction. Maybe we would see quantum storage at some point of time. We have a different system now. But yeah, SPDC itself, what a very small gadget and all the fascinating things it can do in terms of
Absolutely.
communication and entangled photons and all of that is just fascinating.
Fascinating.
Uh,
Fascinating. Absolutely. Absolutely. Uh,
very.
so the inclination of bringing optics and photonics together, because this is a very kind of specialized term. A lot of people do get a little tangled between them, because you work on quantum photonics. For a general kind of viewer and a listener, can you just give us a gist of what is quantum photonics? If you have to just give in simple terminologies, how would you just define that?
Hmm. So quantum photonics would have, of course, quantum and nonlinear optics as the basic, phenomena for that. But it has a lot to do with single photons and also, gadgets which has some electronics also involved.
Yes. Yeah. Mm.
So,
Mm.
like we work a lot with, so we just so there are nonlinear crystals that we work with, which is in free space. And again,
Mm.
very optics kinds of experiments with
Yeah.
lenses and
Lenses. Yeah.
free
Yeah.
space setup.
Mm.
You have your mounts and everything.
Mm.
So that is a more of a quantum optics experiment, and the fun, and we can actually see the Hongo-Mendel and
Yeah.
anti-bunching experiments in a very clean and nice way. It's easy to tackle those experiments. But on the other hand, because of our fiber-based quantum communication experiments, we deal with a lot of waveguide-based sources which are
Mm.
fiber coupled, and then they also have these WDM. So we work a lot with those multiplexing and demultiplexing. It's
Deplexing.
one of
Mm.
our main things, and they are uh, much of it, has to be driven. So there are electronics like involved in all those. So it's together, and there's also a lot of integrated parts that are involved, right? So we do
Absolutely.
silicon,
Absolutely.
we do silicon. I would not say optics, but it's silicon photonics, right?
Mm. Mm.
Things are like nano waveguides of silicon or silicon nitride, and then yeah. So all of these things have to be fabricated,
Fabricated. Yeah.
and yeah, they are like they're just not simple tabletop experiments. So
Exactly.
that's how
Exactly.
I don't know if I could explain it well, but
Yeah.
that's
Yeah.
like
Very nice. Very nice. In fact, yeah, I
because
also feel. Yeah.
where you have an intermingling with a lot of electronics or FPGA, WDM,
WDM.
all those gadgets which are not purely optics gadgets.
Optics carry. Exactly. So there is a component of quantum, there is a component of optics, and there
Uh,
is also a component of
Electronics,
optoelectronics,
optoelectronics.
which comes into picture, and it makes very fascinating. It's a very important area because all devices which will have to be realized in the context of quantum devices, especially from a quantum optics viewpoint, should actually take the route of quantum photonics, right? Because free space has a limitation. You would not be able to really have propagation of light, and also communication channels cannot be just like conventional free space propagation. You'll have to put it through the fiber, like what Joyee also does a lot in her group, and understand the characteristics of light and other things. So, Joyee, as we come close to the kind of conclusion, give us a gist about the kind of questions you have kind of plans to explore and also currently exploring, and what is the kind of areas you want to get into, not only just in terms of quantum photonics, anything beyond that also.
Mhm. So actually, right now in the group, so the broader aspect, so everything is more or less under the umbrella of quantum communication that we are exploring. And so we are doing very interesting things. So in our free space quantum communication experiments, we actually explore different properties of photons, just not polarization. So polarization is actually one key degree of freedom through which
Mm.
you can encode information, and then have this quantum key distribution and quantum communication. So we learn it through we do that encoding through polarization, usually popularly in all the demonstrations that has been also done internationally, most of them.
Mm.
But it has certain limitations, and today we know orbital angular momentum also gives us a big flexibility in
Like,
terms of enhancing the amount of information that we can convey, and also other kinds of things. Now there is also certain like through some techniques we can also have these hybrid qubits, where there
mm.
is a cusp of polarization as well as orbital angular momentum, and in a smart way, if we join them, then we can have certain problems solved. We can circumvent. For example, there are misalignment and rotational issues between two parties which are not sharing a common reference frame. Right. So you have to smartly encode your qubits. If you do them in polarization, and if the two parties, rotate with respect to each other, polarization requires you to respect your vertical and horizontal
Horizon
axis.
axis,
Right.
yeah.
But if two parties are rotating with respect to each other, then there is an information distortion. So in a smart way, with orbital angular momentum, if you try to see things in your j space, which is the total angular momentum,
Mm.
and you
Mm.
can have this I don't know, I mean, if I'm like, so there is so if there is some misalignment in terms of rotation, the OM and the polarization rotate in an opposite manner,
Opposite.
such that the main information content which you're trying to send through the total angular momentum, that is not affected.
Mm.
So this
Mm.
is something that we are trying to look, and this is something that we've recently explored in our group to show this hybrid entangled photons, which is rotationally invariant. So it's like rather, alignment free. So this is one QKD thing, and
Mm.
so one question, or what we are looking forward to, is to um, make our setup a little bit compact and miniaturized, so that you can have it for space applications, or rather more field deployable
Field deployment
applications.
application.
And then one would like to, because we do this in the lab and we want to see it actually in a practical situation. So
Situation,
that is
yeah.
something, how these OM modes would OM and polarization photons, encoded photons, they would work. And that is one question, one big question. And in the fiber-based quantum communication experiment, actually, we have recently seen this for like we have done entanglement distribution, but within lab
Mm.
using 100-kilometer long fiber spools. So this is something that we have demonstrated, and we see that both QBER, QKD, entanglement, everything is, although you're using 100-kilometer long, distances in a fiber, of course, they are like intact. But again, we would like to now see it in a practical situation,
Situation,
in
nice.
a wide scale, or yeah, those are the things that we would, now is the time that we are ready with our gadgets. In some
Mm.
sense, we have to do some polishing, and we would now have it out just to see how they behave, and how these photons, whether fidelity is maintained, and all kinds of information that we would like to exchange, all those things are maintained or not. So there are different properties, right, of all these entangled photons, and everything is again with entanglement, so that inherent security is there in
Mm. Mm.
application, right? That's another because there are many demonstrations which has been, well, internationally, of course, there are many demonstrations already with entangled photons, but yeah.
Wonderful, wonderful. Especially the field deployment would be a very important step going forward, and it also is in sync with a lot of things which are happening in quantum machine and other things also. So yeah, I wish you and
The
your
way to
group
go
all the best.
in, yes, thank you, Pawan. That's one thing, but there are also many fundamental quantum optics experiments
Quantum, yeah.
right now. Having done our things, we are now, you would not imagine, we are
Mm,
doing other things with Hongo Mendel, and we are also learning from our colleagues, and understanding other things. So we're trying to also look at fundamental things. Students are passionate and they keep trying to do these things in the lab, and there are other experiments where it's not easy to um, play with photons that are orthogonally polarized. So it's like
mm,
horizontal and vertically polarized photons behave differently in fibers, as you know, right? They
mm,
have
mm.
different times of travel, and then it's very difficult to do these entanglement and all of these with them. But then how you tackle them in the lab? So these there are many. So all these good things and bigger questions, but there are several layers of
Several layers.
understanding you have to solve within the lab, and yeah.
Fabulous, fabulous. This is so exciting, and I'm very sure there'll be many more interesting things which will emerge as time progresses. So, thank you very much, Joy. It has been an absolute pleasure to really, get to know the journey of how you became a quantum photonics researcher, and also how you fostered your interest. That's a very important lesson for all of us to really take away
And
and understand.
And if I may add one more thing, especially for the
Yes.
students, I would say, which I also keep telling my students, because again, as we all know, right? You also know this, particularly like PhD and that too, and in experimental physics, be it optics or any other
Mm,
experiments, right? Or in general,
mm,
PhD is a very, I would say, um, it's a journey that's not always very smooth. There are
mm.
hurdles, there are ups and downs. You're in your highs, but then you're also in your lows.
Those.
And I think tenacity is something that we all have somewhere in common. And we are sticking to a problem, not giving up, actually. So even if we are failing actually many a times, but tenacity is something that, because otherwise, all brilliant students would go up, or only would go up somewhere,
Yeah,
right?
yeah, yeah.
It's also about I think it's not about giving up a problem. It's just sticking around and, trying to find new ways around it. So that's one thing.
So well put. So very well put. It is not just about the talent, but also the temperament, which
Mm.
always makes a very important kind of progress. And this is something which we have seen many a times, right? So many times. A lot of times, people who are rated as very so-called brilliant, sometimes do not actually go ahead and do a lot of work just because they do not have the tenacity, as you exactly mentioned.
Unfortunate,
Uh,
actually. I
yeah, it's
wish
very
all
unfortunate.
brilliant people would, go up.
Go up.
But
Yeah, yeah,
many of them lose on their way, or maybe they get diverted. I don't know. So,
absolutely.
and I think one should follow their heart.
Hard.
Because
Yeah.
if you're not doing something that you love, for example, for me, it's photons. I
Yeah.
simply love them. My pet is
Oh,
also known as boson.
wow. That's actually, I should mention that Joey also has a wonderful dog. In fact, it's Boson, right? That's the Boson. So wonderful to know that. I'm so glad. I would actually
Do
mention this
something that you love, otherwise it's difficult to carry it along your entire life.
entire life.
Particularly
Yeah.
us, right? We don't have these changes. We are academicians or we are researchers, and we have to follow. It's a same path, I would say. Of course, with a lot of things, vibrant things that are happening, and also in IIT, I would say IIT
Yeah.
gave me an environment to interact
Mm.
with students, young students, like also ICERs.
Yeah. Yeah.
And although our, we are aging, Pawan, but I
Yeah.
think we keep interacting with them, and it's a fascinating environment that way. So I'm
Absolutely,
glad to be a
absolutely.
teacher there. Yeah.
It's a very enriching environment, especially because it also keeps us grounded, because it will actually help us to come back to the level where we have to understand the world every time, which is changing. And in fact, sometimes there's a kind of notion that academia is little rigid, but anybody who is inside and who looks at the changes which happen from inside would have a very different perspective. In fact, of course, a lot of criticism is valid in many times because it can be insular, but there is also a lot to learn, and also there is a sea of humanity which keeps coming or
Oh, yeah.
rolling in,
Oh,
and
yeah.
it actually helps us
One
to.
profession that gives you a lot of respect, I would
Yeah,
say. With
yeah, yeah.
see, I think there's always different kinds of shades, but I think
Hmm.
this is one profession where if you really want, you can have a no nonsense, kind of a career
Career,
that
absolutely,
without yeah, just
absolutely
doing a work which is fascinating,
fascinating.
talking to students. There's a lot of administrative things also,
Hmm.
of course,
Hmm.
we all need to do, but then you get refreshed when you're in the classroom because you
Yeah,
are
yeah, absolutely.
bombarded
But
sometimes with questions in the first year, particularly, and that keeps you green, and I think tells you that you still don't know enough, and
enough,
you go back,
absolutely.
you hunt for the answers to just to explain to them, in a nice way,
Absolutely correct. Absolutely correct. In fact, that's one of the enriching process of being a researcher and a teacher, because this gives you a platform to do both in one single go, and it's always something very important, which actually gets you kind of ticking here.
Very important. And I think one another high in the career. So
Hmm.
all there are many highs of course of achieving things in the lab, and having a great paper and accepted and all of that, but also having a good group, a great group
Absolutely,
with youngsters. And sometimes now I think I am in that high now where I have started learning from my students. I have
absolutely.
this thing too. They are reading actually much more, and of
Well,
course I give them this broad field, and we discuss. We have our group meetings and all. But I think now I have because now I catch up sometimes from them.
hmm, hmm,
Yeah,
hmm.
really into it. And I
Wonderful.
tell
Yeah.
them this is the best part because later on in life maybe we don't have such a peaceful thing
Yeah.
where there's no restriction and you can just go on in the night with your music on. You just
Hmm.
go on figuring things out in the lab and reading, and so that kind of leverage one will not
Yeah.
get
Yeah.
after in your mid.
Absolutely.
Yeah.
Yeah, yeah, because that is a phase of life which actually is very different. Yeah.
Now it's
Wow.
interaction with our kids also that
Yeah, 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 exactly. Precisely right.
learn.
Because all parents have a different perspective. Because it actually changes the whole way of looking at things. You're
Yeah.
absolutely right.
And just like a child again, Pawan, the child that it is within me, I'm actually interested in Aryan's class, class lectures, and I keep asking him, Peter, when are they starting your physics chapters in charge and electricity and
How old is he? How old is he?
So he will turn 11 soon. He's in
Oh,
class
wonderful.
now. Yeah.
Nice,
And
nice.
but I mean all schools have their own regime. So
Nice.
their
Yeah.
schools they have somehow started with the biology chapters. And of course he's learning about plants. He's
Mm.
interested my as long as my mother was there, actually Arun learned a lot from Ma because she was
Yeah,
student
yeah,
of
yeah.
anthropology, again naturally
Yeah.
inclined towards plants and the living things around.
Nice.
So he did those small experiments also with her, with seeds and growing into a plant and all of that. Thankfully, she was there at that time, and I think Aaron picked up a lot. But now, so all those biology chapters are more or less, I think, what their school is trying to do, trying to cover that first, and they have just started with electricity charges, I would say. Charge, what is charge, and magnetism and all of that. And I'm fascinated again. So in that
Fantastic.
sense, I'm after him that let's get down. Let's see. And it's back to
Uh,
physics. We
Like
like to
crazy.
discuss everything.
Absolutely, absolutely. Joy, it has been again absolute pleasure. Thank you very much for your time.
Pleasure
And
for me as well,
yeah,
Pawan.
yeah,
Thanks for
yeah,
having me. I think
yeah,
I
yeah.
just talked and talked and
No, no, no. This is
like
wonderful. So yeah. So this is Pratidwani, where we try to humanize science. This time with the one and the only Joyee Ghosh. Thank you, Joy.
thank you, Pawan. Thank you.